Welcome back to Talk Tensors. You know we love to dig into those cutting-edge machine learning papers, and today we've got a real gem, Guaranteed Recovery of Unambiguous Clusters. It's by Mizzouji and Shomeroni.
Interesting choice, yeah.
It really dives deep into this fundamental problem of clustering.
Oh yeah, clustering. It's everywhere, right? But this one has a twist.
It really gets you thinking.
Yeah.
You know, even when you think you've nailed those clusters, how do you really know you've got the true structure?
That's the million-dollar question, isn't it? And it's something a lot of those standard algorithms kind of gloss over.
Right, they just assume you've got those nice, neat, well-separated clusters.
Yeah, like textbook examples.
But in the real world, it's rarely that clean.
Right.
Right? Think about trying to cluster images of dog breeds. Some of them look so similar.
Yeah, you've got your poodles and your doodles and who knows what else.
Exactly. So how can an algorithm tell them apart reliably?
It's all about navigating that inherent ambiguity. And then you throw in things like varying cluster densities.
Ooh, yeah, that can get messy.
Imagine financial data during a market crash. Suddenly you've got this huge spike in activity.
And a traditional algorithm might see that as a separate cluster, right?
Right, when in reality it's just part of a larger trend that's being distorted by this short-term event.
So they get fooled by the noise.
Exactly. They miss the big picture. And don't even get me started on non-convex cluster shapes.
Ah, yes, those clusters that refuse to stay in their neat little circles.
Like imagine trying to cluster data about islands in an archipelago.
Ooh, I like that analogy.
Right. It's not just about distance. It's about how those islands are connected, those weird shapes.
So the algorithms need to be able to handle that complexity.
Precisely. Now, the authors, they do a good job of laying out those existing approaches. You've got your spectral clustering, which basically tries to simplify things by looking at the data's shadow, so to speak.
I've always loved that way of thinking about it.
It's a powerful technique, but it has its limitations, especially when those cluster shapes get really wild.
Right. And then you've got your density-based clustering. Those are the ones that really try to find those peaks in the mountain range.
Yeah, those high-density areas. But as the paper points out, a lot of these methods lack that rigorous theoretical foundation.
So they might work well in practice, but we don't always know exactly why.
And that's where Mizzouji and Shomeroni come in. They introduce this really cool idea called weak separability.
Weak separability. That sounds intriguing.
It is. It's a way to define when clusters are truly distinct based on their density.
So like if you have two mountains that are close together, but they have a valley separating them.
Exactly. That valley is the key. It shows that those mountains are separate entities, even though they might be close.
I'm starting to see how this connects to the clustering problem.
Yeah, it's all about finding those valleys in the data, those areas of lower density that define the boundaries between clusters.
Okay, that makes sense.
Yeah.
But isn't it possible to have multiple valleys, multiple ways to separate those mountains?
That's the fascinating part. You can actually have multiple weakly separable clusterings for the same data set.
Wow, so just finding any weakly separable clustering isn't enough.
Right. We need a way to find the best one, the one that truly reflects the underlying structure of the data.
And that's where their second big idea comes in, local maximum separability.
Or LM separability for short.
Sounds pretty complex.
Yeah.
What's the intuition behind it?
Imagine you're at a crowded party standing with your group of friends.
Okay, I'm picturing it.
Now, someone from another group might be physically closer to you than some of your own friends.
That happens all the time.
LM separability helps us make sense of that. It's not just about absolute distance. It's about how dense your cluster of friends is compared to other clusters.
So even though that person from the other group is closer to me physically, I'm still more connected to my own group because we're more densely packed.
Exactly. And that's the key insight. It's not just about distance. It's about relative density.
Okay, so LM separability helps us avoid those situations where we misclassify points based on simple distance.
Exactly. It's about understanding the local density landscape.
So how do they actually put these two ideas, weak separability and LM separability, into practice?
That's where their algorithm comes in. They call it the MSCE algorithm.
MSCE. Does it stand for something?
It stands for minimal seed expansion, and it's a really elegant approach. Think of it like scattering seeds in a garden. Each seed represents the starting point of a cluster, and then the algorithm expands around each seed, adding points based on their density relative to the seed.
Okay, I'm seeing the garden analogy come to life here. So if a seed lands in a really dense area.
Right, then you'd use a stricter criteria for adding points to that cluster.
But if it lands in a more sparse area.
Then you can be a bit more flexible.
It's like each seed has its own little bubble of influence.
Exactly. And the size of that bubble is determined by the algorithm's parameters. One of the key parameters is A, which controls how much variation in density you allow within a single cluster.
So A is like a dial we can tweak depending on the type of data we're dealing with.
Precisely. And then you've got M and D, which are all about putting those ideas of weak separability and LM separability into action.
Okay, break those down for me.
So M is the minimum size a cluster needs to be considered valid.
So it's like a quality control check, making sure we're not getting distracted by tiny little clusters that aren't really meaningful.
Exactly. And then D governs the maximum variation and density allowed between different clusters.
So it's like saying, okay, these two clusters might be close together, but their densities are so different that they can't possibly be part of the same structure.
Right. It ensures that you're not lumping together apples and oranges density-wise.
Okay, I'm really starting to appreciate the elegance of this approach. So how did it actually perform? Did it live up to the hype?
Oh, yeah. They put it through its paces. They tested it on a bunch of different data sets, both real world and synthetic, and compared it to some of the big names in clustering.
Like k-means, spectral clustering, all those classics.
Exactly. And the results were pretty impressive, to say the least.
So MSCE came out on top.
In most cases, yeah. Especially when you look at the adjusted RAND index, or ARI, which is a standard way to measure clustering performance.
So it's not just a good idea on paper, it actually works in practice.
Exactly. And what's really cool is how this paper fits into the broader history of clustering research.
Oh yeah, clustering's been around for ages, right?
Decades. It's one of those fundamental problems in machine learning and data analysis.
And we've seen all sorts of different approaches over the years.
Hierarchical clustering, partitioning methods, fuzzy clustering, you name it.
But this paper feels different somehow. It's not just about tweaking an algorithm to optimize some metric. It's about really understanding what makes a good cluster in the first place.
You hit the nail on the head. It's a paradigm shift.
It's like saying, let's not just try to climb the highest mountain.
Right.
Let's first figure out what makes a mountain a mountain.
Perfect analogy. And that's what makes this paper so exciting. It's not just an incremental improvement. It's a fundamental rethinking of the problem.
And that kind of thinking can lead to all sorts of new discoveries and applications.
Absolutely. It's like they've given us a new lens through which to view data.
A new way to uncover those hidden structures.
Precisely. And speaking of new lenses and hidden structures, it's time for our favorite segment.
Novel notions.
That's right. Where we let our imaginations run wild and explore those what-if scenarios.
The possibilities that this research opens up.
Exactly. What really gets me thinking is the potential for clustering algorithms to go beyond just grouping data points.
Oh, to do what?
To actually predict how those clusters might evolve over time.
Whoa, now you're talking. It's like giving those static clusters a life of their own.
Exactly. Imagine applying this to social networks, for example. You could identify communities based on interaction patterns.
Okay, that's pretty standard stuff.
But what if you could go further and predict which communities are likely to grow, merge, or even splinter based on subtle shifts in those patterns?
So it's not just about understanding the snapshot. It's about predicting the movie.
Exactly. And this could have huge implications for understanding social trends, the dynamics of political movements, even how misinformation spreads.
It's making me rethink how we look at dynamic systems in general.
Right. And this goes way beyond social media. Think about financial markets.
You could predict which companies are likely to be acquired or merge based on how their financial data clusters and shifts.
Precisely. Or in healthcare, you could identify patients at risk of developing certain conditions by clustering their medical history and lifestyle factors, and then seeing how those clusters evolve.
The possibilities are endless. But of course, there are challenges.
Oh, yeah, for sure. How do we incorporate this temporal dimension into the algorithms? How do we account for those external factors that might influence how clusters evolve?
Yeah, and how do we ensure that these algorithms are used ethically and responsibly?
All crucial questions. But that's the beauty of cutting-edge research. It pushes us to ask those tough questions.
To think beyond the current limitations.
Exactly. And I think that's where the true value of a paper like this lies. It's not just about the specific algorithm or the impressive results.
It's about sparking those conversations, those what-if moments that can lead to entirely new fields of exploration.
It's giving us a new language, a new set of tools to think about complex systems in a more dynamic way.
Yeah, it's a tightrope walk, isn't it? Pushing the boundaries, but always being mindful of the potential consequences.
For sure. But that's what makes this field so exciting. It's all about finding that balance between innovation and responsibility.
And I think this paper does a great job of highlighting that tension. It's not just about the technical achievements, it's about prompting those broader societal discussions.
Absolutely. It's giving us a new framework for thinking about complex systems in a more dynamic and nuanced way.
But let's bring it back down to earth for a second. Why should our listeners care about this research even if they're not machine learning experts?
That's a great question. It's easy to get caught up in the technical details and forget about the real-world impact.
But the truth is, these algorithms are everywhere, aren't they?
They're shaping our online experiences, personalizing recommendations, informing healthcare decisions, often without us even realizing it.
It's like an invisible hand guiding our digital lives.
Exactly. And that's why it's so important to have algorithms that are accurate, reliable, and fair. This research is a step towards that goal.
It gives us a way to think critically about clustering and develop algorithms that are less susceptible to noisy data or biased assumptions.
So by understanding the principles behind this research, we can be more informed consumers of information and technology.
We can start asking questions about how clustering is being used, whether it's being done ethically and responsibly.
It's about empowerment through understanding.
I love that, and I think that's a perfect note to end on. Any final thoughts before we sign off?
Just that I'm incredibly excited to see where this line of research leads. We're just scratching the surface of what's possible with clustering, and papers like this one are lighting the way.
Well said. Thanks for joining us on Talk Tensors. We hope this deep dive has given you a new appreciation for the power and potential of clustering algorithms. And if you're hungry for more, you can find a link to the full paper in the episode description. Until next time, keep those tensors talking.